Today we're going to look at the limit of log functions. So if you guys know what log functions are, that's great. If you don't, definitely go review them. Review their properties. They're going to be pretty important in this proof. So what we're trying to show is that the limit as x approaches c of log base a of x is going to equal log base a of c. And this is given that c is in the domain of log base a of c. So that means, of course, that, or log base a of x. And for a log function, that means that c is going to be greater than 0, but less than infinity. And also that a is greater than 1. So we're going to prove this for log bases greater than 1, and then we're going to use some of our limit properties to extend that to log bases less than 1. So let's get started. To prove that this limit exists, what we need to show is that for any epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of log based a of x minus log based a of c is going to be less than epsilon. And to do this proof, we're going to have to rewrite some of these inequalities. But the first thing I want to look at is this inequality right here. So what it says is that if we are to pick x values around c in a range c plus delta to c minus delta, not including c, we just have to show that picking x values here in this delta range will return epsilon, or will return log base a of x values around log base a of c values in a range defined by the size of epsilon. For any epsilon, we have to show that this delta exists. So if we were to show that for any x values inside this interval, including c, that we were able to get log base a of x values around log base a of c values defined by the size of epsilon, we would still have shown that in the interval not including c, this still works. And the reason is because the interval not including c is just a subset of the interval including c. So the way we're going to do it is we're going to actually prove it with the interval including c, because that just turns out to be easier. So what we're going to do is rewrite this inequality right here. And these aren't actually the same inequalities, because this next one's going to include the point where x equals c. But it's going to be x minus c is greater than negative delta and less than delta. And again, this looks like something like this, where you have you have c plus delta, you have c minus delta, and this includes all the x values in between c minus delta and c plus delta. And we're going to show that there is some delta for any epsilon, such that when we pick x values in this interval, we get back log base a of x values in that interval around log base a of c. And the way we're going to start doing that is by manipulating this inequality right here. And this inequality over here, let me write this a bit closer, because we're going to need the room. So let me write this again a bit closer. And that's a delta. Let's fix that. That's a delta. And this inequality right here can be written as negative epsilon is going to be less than log base a of x minus log base a of c, less than epsilon. And again, this is just if we had our log base a of x values on a number line. If we had log base a of c, we're going log base a of c plus epsilon and log base a of c minus epsilon. So we're trying to get log base a of x values inside this interval right here. Okay, so that's why we can write that inequality like this. It's just getting rid of that absolute value, makes it a bit easier to work with. And now we're just going to do some math with this, some simple algebra. So we know that if this inequality is true, then we can just work with this, and using our property of logs, when we subtract logs, we can do something like this. And if that looks unfamiliar, definitely review the properties of logarithms. And now what we're going to do is we're going to raise both sides to the power of a. And we get something like this. Or I should say all three sides, because there's three components. And we're going to keep going, just multiply each part of the inequality by c. And there should be a c there as well. And now what I'm going to do is I'm going to subtract c from each part. Now I'm going to go ahead and I'm going to factor that c out of this part of the inequality and the next part as well. So I'm going to factor that c out. And this is going to be -1 as well. And if you look at this expression right here, a to the negative epsilon minus 1, it can be written as 1 over a to the epsilon minus 1, which if we find a common denominator is just going to be 1 minus a to the epsilon over a to the epsilon. So I'm going to write that like that, 1 minus a to the epsilon over a to the epsilon. 1 minus a to the epsilon over a to the epsilon. And here's the key. The key is that if x minus c is greater than this expression right here, but less than this expression right here, then we know that epsilon is greater than the absolute value of log a of x, log base a of x, minus log base a of c. So what we're saying is if this inequality is to hold true, this one that we just algebraed out, then this one would also hold true. And that's really important. Why is that? Well, we can just do the math in reverse to show that this inequality implies this inequality. You know, we just work through that algebra. So now what we're going to do is take a look at what this inequality is. What range of x values does this inequality work for? Well, the first thing we're going to recognize is that a to the epsilon has to be bigger than 1. And that's because of the constraints we set. So we set the constraints that a to the epsilon, or that, sorry, let me just erase that. We set the constraints that a is bigger than 1. If you remember, we set that up here. And we set the constraint that epsilon is greater than 0. We always know that epsilon is greater than 0. And because of that, you can check this, and you can test it all you want, but a to the epsilon will always be greater than 1. And as you can see, what that lets us know is that 1 minus a to the epsilon, because a to the epsilon is going to be greater than 1, will be a negative quantity on the top. And this expression right here will be negative, and this expression right here will be positive. So what I'm going to do is I'm going to pull out a negative from here, and I'm going to write it like this. I'm going to write it like negative c a to the epsilon minus 1 over a to the epsilon is going to be less than x minus c is going to be less than c times a to the epsilon minus 1. So that's our inequality. And now I'm going to do something that might not make sense right now, but it will make sense in just a second. I'm going to say that delta 1 is equal to c times a to the epsilon minus 1 over a to the epsilon. And I'm going to say that delta 2 is equal to c times a to the epsilon minus 1. And I'm going to rewrite this inequality right here as x minus c is less than delta 2, but it's greater than negative delta 1. And if you see, this looks kind of familiar to what we have up here. And if you remember that number line I drew, we can draw out and we can see for what x values does this inequality hold true. It turns out it holds true for x values, as you might have guessed, from c to c plus delta 2 and c to c minus delta 1. Now remember, delta 1 and delta 2 are different sizes. So the sizes of these two spaces are actually different. But we know that if we pick x values, so this is an x value number line, if we pick x values inside this whole interval right here, we will from those x values, if we were to plug those x values into here, this inequality would indeed hold true. So what we're going to do is we're going to pick the smaller of these two. We're going to pick the smaller of delta 1 and delta 2 and set our interval on each side to be based on that side, based on either delta 1 or delta 2, the smaller of the two. And the reason is because let's say delta 1 is smaller, then we keep this the same size and we shrink this side down. Well, how do we know that our x values still work? Because with delta 2, which was bigger, delta 2 was bigger, when we pick that smaller delta 1, we still get all x values that were inside that interval defined by c plus delta 2. So what we're going to do is we're going to pick the smaller of the two and set delta equal to that. So we're going to say delta is equal to the minimum of delta 1 and delta 2. And it's pretty easy to see that if a to the epsilon is bigger than 1, that delta 1 will be smaller than delta 2. So we know that this is delta 1, and we know that it is c times a to the epsilon minus 1 over a to the epsilon. Now, here's the crux of the proof, because we've essentially done it. It's just piecing together and realizing what we've done. We have found an interval of x values such that if I was to draw that interval again right here, where this is my x number line, if I was to go from c to c plus delta 1, or just delta because I've defined it as delta, and c minus delta, if I was to pick any x values inside this whole interval, or maybe even inside the whole interval except at c, so I don't care about c, if I was to pick any of those values around c inside that interval defined by delta, when I plug that x value into this inequality, I would find that this inequality holds to be true. I would find that for that x value, the absolute value of the log base a of x minus log base a of c is less than epsilon. And look at what that delta value equals. That delta value equals c times a to the epsilon minus 1 over a to the epsilon. So essentially, for any epsilon value, you give me any epsilon value, I will give you back a delta value such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of log base a of x minus log base a of c will be less than epsilon. And that delta value I give back will be c times the quantity a to the epsilon minus 1 over a to the epsilon. So if you gave me an epsilon value of maybe 0.01, all I would do is I would plug 0.01 in here for epsilon, plug in my c, plug in my a, and I would have my delta value for that corresponding epsilon value. So we have effectively shown that for any epsilon value, that delta value does exist. All you have to do is take that epsilon value and plug it in right here. So that proves that the limit as x goes to c of log base a of x is equal to log base a of c, provided that c is in the domain of log base a of x and that a is greater than 1. Now we're going to go ahead and try and show this for log bases that are less than 1 but still greater than 0. So we're going to try and show that log base b of x, if we take the limit as x goes to c of log base b of x, we're going to show that that is equal to log base b of c. And we're going to do this with our last proof. We know that the limit as x goes to c of log base a of x is equal to log base a of c. And this is where b is between 0 and 1, and where a was greater than 1. Notice neither of these are at 1. If you have log base 1 is actually only defined at x equals 1. Because if you have log base 1 of x is equal to some number, you're trying to say 1 to what power equals x. Or if I had maybe a better way of showing it is log base 1 of 3 is equal to x, and I'm trying to solve for x. 1 to what power is equal to 3? Well, it's undefined. 1 to no power is equal to 3. The only thing 1 to the x can ever be equal to is 1 itself. So log base 1 isn't something we're really going to look at, and it's not something we're going to be worried about. we're looking at log bases between 0 and 1. Well, here's how we're going to do this. This is what we want to prove. And this is something we've already proved, so we know this is a true statement. All we're going to do is multiply both sides by a constant. And we know, based on our constant rule, that the limit as x approaches c of some constant times a function is going to equal that constant times that original limit of that function. So this is just based on our constant rule. And what we're going to do is say k equals -1. And here's what happens. We get limit as x approaches c of log base a of x is equal to, or negative log base a of x is equal to negative log base a of c. And with our log properties, we can actually rewrite this as log base 1 over a of x is equal to log base 1 over a of c. So if we wanted to find the log base b, all we have to do is find that corresponding a value such that 1 over a is equal to b. So for any number between 0 and 1, we just have to find that corresponding number greater than 1 such that the reciprocal of that number is equal to that number between 0 and 1. And if you guys think about that function f of x equals 1 over x is equal to 1 over x, and you think about what it looks like, well, at 1, at x equals 1, y is also equal to 1, and it looks something like this. So we get all these values between 0 and 1, where f of x right here is between 0 and 1 when x is greater than 1. So as long as we can find that corresponding a value such that 1 over a is equal to b, we can say that the limit as x goes to c of log base b of x is equal to log base b of c.